there's a beyond bizarre link between quantum physics and the human mind. This is unbelievable. I cannot define the real problem, therefore I suspect there's no real problem, but I'm sure there's no real problem. The American physicist Richard Feynman said this about the notorious puzzles and paradoxes of quantum mechanics, the theory physicists use to describe the tiniest objects in the universe, but he might as well have been talking about the equally knotty problem, knots that is, of consciousness. Some scientists think we already understand what consciousness is, or that it is a mere illusion, but many others feel we have not grasped where consciousness comes from at all. The perennial puzzle of consciousness has even led some researchers to invoke quantum physics to explain it. That notion has always been met with skepticism, which is not surprising. It does not sound wise to explain one mystery with another, but such ideas are not obviously absurd, and neither are they arbitrary. For one thing, the mind seemed, to the great discomfort of physicists, to force its way into early quantum theory. What's more, quantum computers are predicted to be capable of accomplishing things ordinary computers cannot, which reminds us of how our brains can achieve things that are still beyond artificial intelligence. Quantum consciousness is widely derided as mystical woo, but it just will not go away. Quantum mechanics is the best theory we have for describing the world and at the nuts and bolts level of atoms and subatomic particles. Perhaps the most renowned of its mysteries is the fact that the outcome of a quantum experiment can change depending on whether or not we choose to measure some property of the particles involved. When this observer effect, quote unquote, was first noticed by the early pioneers of quantum theory, they were deeply troubled. Because it doesn't make sense. It seems to undermine the basic assumption behind all science, that there is an objective world out there, irrespective of us. If the way the world behaves depends on how, or if we look at it, what can reality really mean? So the world depends on how we look at it. Is that real? I mean, is my reality the same as your reality? Obviously no. Now, some of those researchers felt forced to conclude that objectivity was an illusion, and that consciousness has to be allowed an active role in quantum theory. To others, that did not make sense. Surely Albert Einstein once complained the moon does not exist only when we look at it. Today, some physicists suspect that, whether or not consciousness influences quantum mechanics, it might in fact arise because of it. They think that quantum theory might be needed to fully understand how the brain works. Might it be that just as quantum objects are apparently in two places at once, so a quantum brain can hold on to two mutually exclusive ideas at the same time? These ideas are speculative, and it may turn out that quantum physics has no fundamental role either for or in the workings of the mind. But if nothing else, these possibilities show just how strangely quantum theory forces us to think. The most famous intrusion of the mind into quantum mechanics comes in the double slit experiment. Imagine shining a beam of light at a screen that contains two closely spaced parallel slits. Some of the light passes through the slits, whereupon it strikes another screen. Light can be thought of as a kind of a wave, and when waves emerge from two slits like this, they can interfere with each other. If their peaks coincide, they reinforce each other, whereas if a peak and a trough coincide, they cancel each other out. This wave interference is called diffraction, and it produces a series of alternating bright and dark stripes on the back screen where the light waves are either reinforced or cancelled out. This experiment was understood to be a characteristic of wave behavior over 200 years ago, well before quantum theory existed. The double slit experiment can also be performed with quantum particles like electrons, tiny charged particles that are components of atoms. In a counterintuitive twist, these particles can behave like waves. That means they can undergo diffraction when a stream of them passes through the two slits, producing an interference pattern. Now suppose that the quantum particles are sent through the slits one by one, and their arrival at the screen is likely seen one by one. Now there is apparently nothing for each particle to interfere with along its route, yet nevertheless the pattern of particles impacts that builds over time reveals interference bands. The implication seems to be that each particle passes simultaneously through both slits and interferes with itself. This combination of both paths at once is known as superposition state. But here's the really odd thing. If we place a detector inside or just behind one slit, we can find out whether any given particle goes through it or not. In that case, however, the interference vanishes. Simply by observing a particle's path, even if that observation should not disturb the particle's motion, we can change the outcome. Can you believe that? Now, the physicist Pascual Jordan, who worked with quantum guru Niels Bohr in Copenhagen in the 1920s, put it like this: observations not only disturb what has to be measured, they produce it. We compel a quantum particle to assume a definite position. In other words, Jordan said, we ourselves produce the results of the measurements. If that's so, objective reality seems to go out of the window. And it gets even stranger. If nature seems to be changing its behavior depending on whether we look or not look at it, we could try to trick it somehow showing its hand. To do so, we could measure which path a particle took through the double slits, but only after it's passed through them. By then, it ought to have decided whether to take one path or the other. An experiment for doing this was proposed in the 1970s by an American physicist, John Wheeler, and this delayed choice experiment was performed in the following decade. It used clever techniques to make measurements on the paths of quantum particles, generally particles of light called photons, after they should have chosen whether to take one path or a superposition of two. It turns out that, just as Bohr confidently predicted, it makes no difference whether we delay the measurement or not. As long as we measure the photon's path before it arrives at a detector is finally registered, we lose all interference. It's as if nature knows, quote unquote, not just if we're looking, but if we're planning to look. I mean, this is bizarre. This is bizarre. I mean, that means nature has a consciousness bigger than ours. Anyway, whenever in these experiments we discover the path of a quantum particle, its cloud of possible routes collapses into a single well-defined state. What's more, the delayed choice experiment implies that the sheer act of noticing, rather than any physical disturbance caused by measuring, can cause the collapse. But does this mean that true collapse has only happened when the result of a measurement impinges on our consciousness? That possibility was admitted in the 1930s by the Hungarian physicist Eugene Wigner. He said it follows that the quantum description of objects is influenced by impressions entering my consciousness. He wrote, solipsism may be logically consistent with present quantum mechanics. Wheeler even entertained the thought that the presence of living beings which are capable of noticing has transformed what was previously a multitude of possible quantum pasts into one concrete history. In this sense, Wheeler said, we become participants in the evolution of the universe since its very beginning. In his words, we live in a participatory universe. To this day, physicists do not agree on the best way to interpret these quantum experiments. And to some extent, what you make of them is at the moment up to you. But one way or another, it's hard to avoid the implication that consciousness and quantum mechanics are somehow linked. Beginning in the 1980s, a British physicist Roger Penrose suggested that the link might work in the other direction, whether or not consciousness can affect quantum mechanics. He said, perhaps quantum mechanics is involved in consciousness. What if, Penrose asked, there are molecular structures in our brains that are able to alter their state in response to a single quantum event? Could not these structures then adopt a superposition state, just like the particles in the double slit experiment? And might those quantum superpositions then show up in the ways neurons are triggered to communicate via electrical signals? Penrose says maybe our ability to sustain seemingly incompatible mental states is no quirk of perception but a real quantum effect. After all, the human brain seems able to handle cognitive processes that still far exceed the capabilities of digital computers. Perhaps we can even carry out computational tasks that are impossible on ordinary computers, which use classical digital logic. Penrose first proposed the quantum effect features in human cognition in his 1989 book, The Emperor's New Mind. The idea is called OR, which is short for Orchestrated Objective Reduction. The phrase objective reduction means that, as Penrose believes, the collapse of quantum interference and superposition is a real physical process like the bursting of a bubble. OR draws on Penrose's suggestion that gravity is responsible for the fact that everyday objects such as chairs and planets do not display quantum effects. Penrose believes that quantum superpositions become impossible for objects much larger than atoms because their gravitational effects would then force two incompatible versions of space-time to coexist. Penrose developed the idea further with American physicist Stuart Hameroff. In his 1994 book Shadows of the Mind, he suggested that the structures involved in the quantum cognition might be protein strands called microtubules. These are found in most of our cells, including the neurons in our brains. Penrose and Hameroff argue that vibrations of microtubules can adopt a quantum superposition. But there is no evidence of these things, such a thing as remotely feasible. It's been suggested the idea of quantum superposition in microtubules is supported by experiments described in 2013, but in fact those studies made no mention of quantum effects. Besides, most researchers think that OR idea was ruled out by a study published in 2000. Physicist Max Tegmark calculated that quantum superpositions of the molecules involved in neural signaling could not survive for even a fraction of time needed for such a signal to get anywhere. Quantum effects such as superposition are easily destroyed because of a process called decoherence. This is caused by the interactions of quantum objects with its surrounding environment, through which the quantumness leaks away. Decoherence is expected to be extremely rapid in warm, wet environments like living cells. Nerve signals are electrical pulses caused by the passage of electrically charged atoms across the walls of the nerve cells. If one of these atoms was in a superposition and then collided with a neuron, Tegmark shows that the superposition should decay in less than a 1/billionth of a second. It takes at least 10,000 trillion times as long for a neuron to discharge a signal. And as a result, ideas about quantum effects in the brain are viewed with great skepticism. But Penrose is unmoved by those arguments and stands by the OR hypothesis, and despite Tegmark's prediction of ultra-fast decoherence in cells, other researchers have found evidence for quantum effects in living beings. Some argue that quantum mechanics is harnessed by migratory birds that use magnetic navigation, and by green plants when they use sunlight to make sugar in photosynthesis. Besides, the idea that the brain might employ quantum tricks show no sign of going away, for there is now another quite different argument for it. In a study published 2015, physicist Matthew Fisher of University of California, Santa Barbara argued that the brain might contain molecules capable of sustaining more robust quantum superpositions. Specifically, he thinks the nuclei of phosphorus atoms may be having this ability. Phosphorus atoms are everywhere in living cells. They often take the form of phosphate ions, in which one phosphate atom joins up with 4 oxygen atoms, and such ions are the basic unit of energy within the cells. Much of the cell's energy stored in molecules called ATP, which contain a string of 3 phosphate groups joined to an organic molecule, and when one phosphate is cut free, energy is released for the cell to use. Cells have molecular machinery for assembling phosphate ions into groups and cleaving them off again. Fisher suggests a scheme in which two phosphate ions might be placed in a special kind of superposition called an entanglement state. The phosphorus nuclei have a quantum property called spin, which makes them rather like little magnets with poles pointing in particular directions. In an entangled state, the spin of one phosphate nucleus depends on that of the other. Put another way, entangled states are really superposition states involving more than one quantum particle. And Fisher says that the quantum mechanical behavior of these nuclear spins could plausibly resist decoherence in human timescales. He agrees that Tegmark that quantum vibrations, like those postulated by Penrose and Hameroff, will be strongly affected by their surroundings and will decohere almost immediately. But nuclear spins do not interact very strongly with their surroundings. And all the same, quantum behavior in the phosphorus nuclear spins could have been protected from decoherence, he says. In Posner's molecules, Fisher argues phosphorus spins could resist decoherence for a day or so, even in living cells. It means they could influence how the brain works. The idea is that Posner's molecules can be swallowed up by neurons, and once inside, the Posner molecules could trigger the firing of a signal to another neuron by falling apart and releasing their calcium ions. He first got this idea when thinking about mental illness and lithium drugs. In 2016, Adrian Kent, University of Cambridge in the UK, one of the most respected quantum philosophers, speculated that consciousness might alter the behavior of quantum systems in subtle but detectable ways. Kent is cautious about the idea. He says there is no compelling reason of principle to believe that quantum theory is the right theory in which to try to formulate a theory of consciousness, or that the problems of quantum theory must have anything to do with the problem of consciousness, he admits. But he says that it's hard to see how a description of consciousness based purely on pre-quantum physics can account for all of the features it seems to have. One particularly puzzling question is how our conscious minds can experience unique sensations, such as the color red or the smell of frying bacon. With the exception of people with visual impairment, we all know what red is like, but we have no way to communicate the sensation, and there's nothing in physics that tells us what it should be like. Sensation is like this are called qualia. We perceive them as unified properties of the outside world, but in fact they are products of our consciousness, and that's hard to explain. Indeed, in 1995, philosopher David Chalmers dubbed it the hard problem of consciousness. Every line of thought and the relationship of consciousness to physics runs into deep trouble, says Kent. So he eventually bravely estimates the chances of finding. Says, I would give credence perhaps 15%, something specifically to do with consciousness causes deviations from quantum theory, with perhaps 3% credence this will be experimentally detectable within the next 50 years, he says. If that happens, it would transform our ideas about both physics and the mind. That seems a chance worth exploring. This is by Philip Ball and BBC and a Sun-Bended Reality. Please leave your comments and thank you for your support. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.